Good morning, everyone. My name is Nicola De Blasio, and it is my pleasure to welcome you to the Global Energy Transition Talk series. Today, we will look into the future of sustainable plastic, or in other words, how to leverage the advantages of plastic without contributing to the world's environmental crisis. And we will do so with the help of a panel of superstars. Let me briefly introduce each of them. First, Blake Beckstein, who is program manager at the Defense Advanced Research Project Agency, DARPA. Blake joined DARPA in 2016 and has served twice as acting deputy director for the Biological Technology Office. He focuses on novel approaches to addressing issues facing agriculture, biotechnology, and food security. Additionally, Blake works on climate-conscious approaches to infrastructure development and waste elimination, utilizing cutting-edge synthetic biology platforms. Blake has received many awards, including the University of Texas System Regents Outstanding Teaching Awards and the Tyler President Scholarly Achievement Award. Alessio Lorusso is the founder and CEO of Roboze, which designs and manufactures the most precise 3D printing technology in the world for high-performance superpolymers and composites. Alessio built his first 3D printer when he was only 17 and invented the beltless technology a few years later. Roboze materials can be used for metal replacement in applications such as aerospace, defense, energy, or medical devices. Alessio was named the 2019 Entrepreneur of the Year by Ernst Young and is part of the Forbes 30 Under 30 class of 2018. Last but not least, I would like to introduce Phoebe Fallon, my research partner in this endeavor. Without Phoebe's unwavering determination, focus, attention to detail, and dry sense of humor, our research project on the future of plastic would have proceeded at a much slower and boring pace. Phoebe will start by presenting our study results and conclusions. She will then be followed by Blake, who will discuss a resource, DARPA's program on using plastic for fuel and food production, and will give us other example of DARPA's cutting-edge research. Alessio will then share with us how 3D printing is enabling manufacturing on demand, the role of plastic, and what Roboze is doing in respect to its sustainability. We will then end with a Q&A session. Before I hand it over to Phoebe, I would also like to thank Liz Enlow for organizing this webinar. So let me start to share. Here we go. Share. Here, Phoebe, all yours.
Thank you, Nicola. Thank you for the introduction, and hello, everyone. Today, I'm going to be talking a little bit about our research paper, which we completed a couple years ago. So since the inception of the plastic industry, more than 6.3 billion tons of plastic waste have been produced worldwide, the vast majority of which ends up in landfills. Plastic remains in the environment for hundreds of years, and even when degraded, does not leave an ecosystem, but instead remains present as smaller pieces or particles. The structure of the plastic value chain is one of the causes for the global waste crisis, which has been created by plastic. The linear economy approach, which is pictured on the left, is also known as a take, make, waste value chain, in which raw materials are transformed into products that are then used until being thrown away as waste. This model creates value by manufacturing and selling as many products as possible at the cheapest cost possible, and assumes that the planet's resources are infinite. As a result, it does not take into consideration any end-of-life issues. In order to curb the amount of plastic discarded as waste every year, a new approach is needed. Achieving a long-term, sustainable future for plastic will require integration along the entire value chain, from design to reuse, together with the transition to a circular economy. A circular economy, which is pictured on the right, is characterized by a value chain approach in which a product's end of life is taken into consideration from the moment it is developed, and resources are reused instead of being continuously added. In order to improve the plastic value chain and eventually transition to a circular economy for plastics, existing recycling processes need to be streamlined and improved. Today's plastic economy is highly fragmented. Nicola, next slide, please. Thank you. Today's plastic economy is highly fragmented. To begin with, not all plastics are equal, as they have different chemical physical properties and lifespans. These differences are exacerbated by the lack of global standards and coordination across the value chain, which has allowed for the proliferation of different materials, labeling, collection schemes, sorting, and reprocessing systems, all of which hinder overall sustainability. Furthermore, innovation activities are also fragmented. The design of new materials is often disconnected from the development and deployment of after-use processes and infrastructure. Due to the state of the plastic economy, the only widely adopted technology for the large-scale treatment of plastic solid waste today is mechanical recycling, or chop and wash. In this process, plastics are sorted by material type, ground, washed, and then dried to produce recycled flakes. But due to the high temperatures used, progressive material deterioration becomes an issue. The resulting flakes are then usually blended with virgin plastic of the same type to produce materials with suitable properties for manufacturing. Recycling is dictated by market demand, price, and regulatory considerations, and these factors have prevented the wide-scale adoption of an alternative approach to chop and wash, which is chemical recycling. Chemical recycling is a process encompassing various technologies such as pyrolysis with a high tolerance to mixed and contaminated plastic waste streams. The goal of chemical recycling is to break the long polymer chains down into their original building blocks, or monomers, which can then be used as feedstocks for new plastics, fuels, waxes, or other valuable products. It yields materials of higher quality than those obtainable through simple mechanical recycling. However, this approach requires complex industrial processing equipment, and hence overall economics tend to be less favorable compared to the production of virgin plastic. As a result, this route is not yet followed at an industrial scale globally. And both mechanical and chemical recycling have drawbacks, and in some instances are not cost effective when compared to the production of virgin plastic. So up until now, the strategy to address the challenges associated with plastic production and use has been mainly based on the 3 Rs approach: reduce, reuse, and recycle. And although any measure to curb the environmental impacts of plastic is a step in the right direction, a systematic change is needed. With this in mind, our recommendations for the plastic value chain are as follows. First, increase the recyclability of plastics. This can be done by redesigning products to be easily recycled and reused. For example, instead of combining many types of plastic in one product, which makes recycling more difficult and expensive, redesign production so that manufactured goods are made of only one type of plastic. Imagine your Poland Springs bottle if it were just one type instead of 3. Limit the number of specialized plastics and additives and introduce extended producer responsibility to create incentives for plastic products to be easily recyclable. Second, enhance recycling systems themselves. Improve and harmonize existing collection and recycling systems to instate a better infrastructure to accommodate the proliferation of bioplastics. This can be done, for example, by increasing access to industrial composting plants. Mandate recycling targets and percentages of recycled materials in new products. Third, decarbonize production. Switch to low carbon energy sources such as renewable energy or green hydrogen, while substituting petroleum-based plastics with more sustainable materials such as bioplastics. In addition, continue to conduct life cycle analyses on new products to ensure that their overall sustainability. To facilitate these actions, we recommend the development of new public-private partnerships. Foster government support for research and development, either through investment mechanisms or private-public partnerships. Align incentives, for example, by requiring producers to address the negative externalities of plastic waste, such as ocean cleanup. On a larger scale, develop global partnerships that combine technical and regulatory factors to harmonize value chains. Finally, to include consumers in the effort to improve the value chain, we recommend a concerted approach to demystify the plastic sector and ensure that local communities and the public at large have appropriate appreciation for the critical role they play. Educate consumers on plastic life cycles and incentivize sustainable practices, as the way that plastic products are used and disposed of has a significant impact on their value and quality post-use. The transition to a sustainable future for plastic must encompass every aspect of the value chain, from production to consumption to disposal, and be based on a circular economy approach to ensure meaningful and overall positive effects. Thank you.
Thank you, Phoebe. Blake, let me get your slides. Here we go. Almost there. Here we go.
Excellent. And you can go ahead and go to the second slide. There it is. Thank you guys so much for the invitation to come and speak. Of course, very excited and passionate about some of the issues that Phoebe just mentioned. And it's actually where we started with this project, sort of thinking about the problem and looking at ways that we could contribute to a solution. So I work for the Defense Advanced Research Projects Agency. I'm in the Biological Technologies Office. And so, we're the agency, I'll tell you a little bit at the end, but we're the agency that, developed the first ARPANET that became the internet. The Moderna vaccine, that was a BTO, DSO funded project out of DARPA. So there's a lot of pieces, especially in the early stages of research, where DARPA has had a hand. So a lot of times when I give talks, it's anything cool that you've seen, DARPA probably had some role in the development. So this project in particular, I think was really interesting because it came from a couple of places. Number one, the U.S. military produces a very large amount of refuse, and a lot of that happens to be plastic. And so we're a contributor to the current problem. And as we were sort of developing the concept, I was also in Hawaii, where my sister lives, and noticed that on the island of Kauai, there was a bay, and it was just filled with ocean plastic. And I thought there has to be a way that we can contribute to solving this issue. And I think at the same time, I saw a video on Facebook probably that had somebody that was collecting plastic in the ocean. And I thought, well, if you solve half a problem, you don't solve a problem, because they still have to pick that material up, move it somewhere, and now you're just moving the problem from one place to the other. So what we were interested in was solving a military problem, or a problem that we actually contribute to, and maybe take that burden and turn it into higher value products at the end of the sort of logistical chain. And then I've always been interested in reduced logistics, because I think that also contributes to a lot of the climate change events that we've seen. So if we can lower the amount of plastic that's being used, you reuse it in a more beneficial way, and then also reduce sort of the movement of materials around the globe, I think we can help in a lot of different ways. So the way we thought about it really started with an Mre packaging, and I don't know how many of you are familiar with this, but this is a meal ready to eat. So contained in this package is a lot of individually packaged plastic that has food in it. This one is fettuccine Alfredo, which I've tried before and it was delicious. But the plastic that's used, there's 3 different plastics, multi-layered plastics, so it's actually difficult to break down. But what was really cool about this is when you do the math and the chemistry, this packaging actually contains more caloric value than the food that's contained inside of it. So as we were thinking through the molecular, sort of the biochemistry of plastic, we saw that we have a value we can push towards, which would be food products and caloric intake. And so on this little figure that I have up on the screen, it sort of has the 4 steps that we're thinking about. So the first one is the physical release of the chemical structures. So one of the beautiful things about plastic is that it's made of these long chained hydrocarbons that fold back on themselves and don't allow water access. So that reduces catalytic activity, enzymatic activity, biological activity. And so we were interested in thinking, okay, if we can open up those structures, we may have a way to get to a breakdown process molecularly. And so the resource program isn't focused on reshaping existing plastic into new materials, but rather at the molecular level, can we open up structures? Can we allow enzymatic or catalytic activity to break those structures into small 8 to 14 carbon chains that could potentially have value themselves as petroleums, oils, lubricants, and so there may be a value there in just breakdown. But could we also go towards the buildup of new products? And as the food and agriculture guy at DARPA, I was pretty focused on how we would go about doing that. So we were looking at building up products using synthetic biology, looking at microbes that can take that 8 to 14 carbon structure, use that as an energy source, and then develop proteins, fats, carbohydrates in different ways in cellular material that could be harvested at the back end and the recapture of this value. We have to think a lot about, food products coming out, FDA approval for what we're putting together. Sometimes these plastics have toxins in them that we need to make sure that we remove, but ultimately getting to this macronutrient place. And so that's sort of the basis of the whole program. When I was developing it, we had also recognized a scenario in disaster relief where we have some aircraft that can get in scenarios, but it's harder to take off. You need more runway for takeoff than you have for landing. And so our vision was something that was small, portable, that we could get on location. So we have two concepts. One of them is a very small fit in the back of a pickup kind of concept. The other is a larger fit in a Connex box for delivery out of large aircraft like a C-17. And the idea was you could drop that in a place where you have disaster relief needs. You could put trash in one end of the process, and then you have food that comes out at the back end. And we recently funded some work where we're looking at this output product that we're getting and determining whether or not we could hand that over to a 3D printing platform that I have a feeling we're going to hear a little bit about 3D printing in a minute. But could we turn that into very dynamic food products? So not taking the product of resource and turning it into, squishy gummy bears that are printed in different shapes, but could we print dynamic structures using this print material that would give us, say, an apple that would have a skin, have the fruit on the inside, and maybe some additional structure. So if you go to the next slide, I think I'm just framing the argument a little bit more here. Where our current waste stream, large problem that we have, where a lot of things in the military comes down to burn pitting. There have been some attempts at gasification, pyrolysis type approaches, but like Phoebe said, those become arduous and difficult. And then you also have off-gassing that you have to be concerned with. Current state of the art in breakdown of plastic and turning it into new materials is also very large, energy intensive. And so we wanted to get away from that, something that would use recovered energy out of the system itself to feed back into operation. You can go to the next slide. And so the plastic project is something that I'm passionate about, but we have other material projects that we've been working towards. One is looking at alternative sources of natural rubber. You guys may not be aware, but 99% of natural rubber comes from Southeast Asia. 98% of that actually comes from a single species of tree. So we wanted to look at some alternative sources. There's 3 plants that grow in North America, but there is no industry for them to grow into. So we're looking at developing some synthetic biology, increase in rubber production, latex production, and natural plants that are North American, and developing an industry that may alter our need for utilization of international rubber sources. They also have a problem because of the single source of a tree. There's a current fungal outbreak in Southeast Asia that's going to impact the rubber market coming up. So I want to insulate ourselves against that. And then I'll just tell you really quick in 1 minute, another approach that we have. You can flip through the, so we also just completed actually a program called Engineered Living Materials, or the ELM program. And the idea here, I think also is something interesting within this conversation, where we're thinking of alternative materials to meet our needs. So what else can we use besides plastic to accomplish some of the work that plastic gives us? And you can go to the next slide, just show quickly sort of the process that we have, where we're using microbes in different ways that can start to produce some of the materials of need. In this figure, it's actually a microbe that produces calcite, which is taking in carbon dioxide and calcium from the environment and putting those molecules together, export outside of the cell. When it oxidizes, it hardens. And that hardening leads to basically formation of limestone. So we have products like this brick that I have right here. That's an actual, no kidding, brick that gives us an opportunity to produce materials in a different way. And in the case of this brick, this is also on the right side of the carbon equation. So we're pulling in and capturing carbon instead of putting it out into the environment as natural concrete does, or not natural, that traditional concrete does. We also can port this type of idea with other organisms. One example is in fungal growth. We funded a team in Elm that takes fungal mycelia. So if you think of mushrooms, you see the above ground structure that's reproductive, but you have the vegetative structure, the mycelia that looks like roots that grows underground. They could grow the mycelia alone, and this ended up as sort of a foam type replacement. So something that plastic and petroleum based foams have been very popular and cheap to make. If you compress that material, they also make a leather-like material that pretty cool, could be used. Stella McCartney actually took this to Fashion Week in Italy and had a fungal mycelia dress, I think, or parts of the dress. They also make shoes. You can also put filler in with that fungal mycelia and end up with something similar to insulation that can be hardened into something similar to fiberboard. So lots of dynamic uses of these different structures, and different ways that we can get rid of waste and produce new materials from those byproducts, and then rethinking the entire production and material space, thinking about biology from the beginning. So I think I'll stop there because I know I'm a little ahead of time, but maybe Nicola, if you can go to slide number 9. Yeah, so this is just kind of a good way to end a DARPA conversation. This is the way that we think in the building. So if you ever have a chance to come to DARPA or talk to somebody like me, these are the questions you should ask yourself about a new idea as you're developing it. They came from a DARPA director back in the 70s, but they're very simple questions. And when you start at DARPA, you think they're kind of silly. And then all of a sudden, it becomes your mantra. Very clearly articulated, what are you trying to do? Think about how it's done today and what are the limitations of how we're doing it. What's new about your approach? If you're successful, who's going to care? And then think about, sort of the procedural things. What are the risks? Where are you going to have failure points, and how can you mitigate that? How much is it going to cost to do the work that you need to do? How long will it take? And then in DARPA projects, we look at midterm and final exams where we don't just hand over money like other agencies. Instead, we hand over money, and then every month you tell us what you did in the last 4 weeks and what you're going to do with our money for the next 4 weeks. So we're great stewards of the public's money. So with that, I'll stop. I know we have other speakers and then some Q&A that seems like it'll be a whole lot of fun. So again, thanks. I really appreciate the opportunity to be here.
Thank you, Blake. Alessio, next goal is to do 3D printed tiramisu.
Yeah, we're working on, Nicola. We're working on. I will share my screen. Could you please just confirm that you can see that?
Yes.
Fantastic. So first of all, thank you so much, Nicola, Phoebe, for inviting me and give us the opportunity to tell to the audience what we're doing and why we think that our technology can have an impact. My name is Alessio Lorusso. I'm the founder and the CEO of Roboze. I founded Roboze back in 2013 to follow the dream to create the most precise 3D printers. But with time and experience, I think that now we are doing much more than that. Now we are really helping companies in replacing traditional methods in bringing back manufacturing back to the point of use, back to Europe, back to America. few numbers and few things about us. At this point, Roboze employs more than 120 employees between Italy and America. We are based in the south of Italy in a very nice city called Bari and in Houston, Texas. At this point, we have more than 500 printers in 28 countries in the world. And we calculated that our customers in the last 2 years printed more than 50,000 parts in the world. What we do with
Alessio, if you're moving the slides, I don't see them moving though. I don't know the others.
Do you see the slides moving now?
No. So let me do this. I'll.
Can you share?
Yes.
Okay,
you can stop
wonderful.
sharing and I'll do it from here and see if it works. Okay. Here we go. Hold on. I just need to put it full screen.
Typical problems of live streaming events.
Now it's just that I cannot get rid of the taskbar, so I cannot put it full screen right now. But okay.
Fantastic.
This one here. While you talk, I'll try to fix it.
Thank you, Nicola. Thank you. So, what we are doing at Roboze is to distribute the manufacturing in the world. We are creating hundreds of micro factories in the world, which can produce parts just in time, on demand and close to the point of use. Our vision is to bring manufacturing back to the point of use. So back to Europe, back to America in a special way. At this point, we have more than 25 micro factories in 3 continents. And we plan to have additional 20 micro factories at the end of this year. The goal is to print parts just in time, on demand, using the resources needed for producing those parts, avoiding all other waste of material, shipping, CO2 emissions related shipping, and all other stuff involved in this process. We want print parts when needed, where needed, and deliver part close to the point of use. This is the vision behind our business model. Could you please go ahead, Nicola? So at this point, Roboze serves some of the major industry leaders in the world. We serve the major aerospace, automotive, motorsport, defense, medical, and space companies in the world. These companies are using our technology, which is considered the most precise and repeatable 3D printing technology, to print some of the most performing superpolymers and composite materials. But this is not enough for us, because I firmly believe that 3D printing can be part of the solution to reduce the CO2 emissions related to mass manufacturing and irresponsible use of resources. But 3D printing can also become part of the problem if we don't act today to avoid that 3D printing is going to become part of the problem. To reduce the problem today, we need to figure out a way to make 3D printing sustainable for our customers. And I firmly believe that the real environmental sustainability comes when we first create financial sustainability for the companies involved in the sustainability and for the customers of those companies. For this, we created a model, a business model, where we do incentivize our customers in shipping back to us parts at the end of the life cycle. So we can recycle and we can provide materials to them at a fraction of the cost. We want to incentivize customers in using our machines, in printing parts when needed, where needed, and close to the point of use, and ensuring them that those parts will be recycled at the end of the life cycle. Because if we don't care today, we are going to be part of the problem tomorrow. So this business model allows our customers in recycling parts at the end of the life cycle. And this is helping customers in printing parts just in time, in printing parts on demand, and in reducing the carbon footprint of our customers. But this is still not enough, because in the couple of years, we are going to invest millions in the development of biopolymers and biocomposite. I firmly believe that the future of industry will pass through the invention of biopolymers capable to replace oil-based polymers. Simple? It's not simple, because it's not simple, because today biopolymers are used to do very simple and stuff, you know, bags for supermarket and other things that are not going to change the world. But we need to invent, and we need to invest without if and without, you know, limitation, to create the future of biopolymers, because biopolymers can be the real solution for the plastics pollution and the recycling of plastics. I firmly believe in this, and Roboze is committed to invest millions in a couple of years in creating biopolymers and in biocomposite high performance, because the goal is to be part of the future generation of the discoveries of the human beings. We need to be there with the space companies, with the medical companies, to invent the future of biocomposite and biopolymers that can play a very important role in with the most challenging applications for the human beings for the next 20 years. Yes, so I'll be more than happy to respond to the questions and the feedbacks. And again, thanks for inviting me, and thanks for giving us the opportunity to tell what we are doing and why we are very committed in making 3D printing the real future of manufacturing, but in a responsible way.
Thank you. I hope I showed all the slides I had to show, Alessio. If not, I'm sorry. Okay, so let me start with some questions. Blake, can you please hold on, because I wrote it down and now I don't find it, obviously. Can you please describe in a little more detail how the process from going from plastic waste to food works? And then Alessio, you need to add on that one and tell us how and if you could actually 3D print an apple that you can actually eat.
Yeah, so yeah, I can sort of jump in. We the way we approach DARPA projects is I would say that we give guardrails. We have a concept that we want to execute on, and we realize that we have a lot of talented, smart, ingenious people out there that have good ideas. We go in with an idea of how we would like to do it. In my case, I really wanted something that would use synthetic biology through the entire process. That way, you have a way to really conserve energy and put yourself in a good position to be successful. But then as proposals came in, we make evaluations and determine, different ways. And like I said, at the end, we want to mitigate, some of those risks. So you want to take multiple shots on goal, not to use too many cliches here, but what we've been really looking at is different approaches for breakdown. And so there's catalytic approaches that we have some of our researchers doing, things that are activated by very low energy, targeted heat approaches. And we actually had an interesting outcome on one of them. The program's been up and running for about a year. And I have a colleague, Eric Van Giesen, who's running a program called PPB, which he's rethinking personal protective equipment in sort of a new biology focused way. And as part of that, they're producing some new materials that looking at it are going to produce new problems for us, because these materials are going to be even more difficult to break down. And he gave a talk and had somebody from the WHO that brought up the fact that during COVID, we've been producing 42 million tons more plastic trash just from medical waste. And I think that was on a weekly basis. Whatever it was, it's way too much. And turned it to us and said, hey, can you start to break down your stuff? And it turns out all the plastics we're working with are the medical waste plastics. And so using that sort of physics-based approach, I think we have a low energy, good outcome approach that breaks some of those materials down. It also happens to decontaminate, which is a nice piece to it. But we have a lot of different ways. We've also been looking at microbes. So because now we're at a point where we've had dumps in place with plastic there for about 50 to 70 years, we've started to see evolution come up with approaches for breaking these materials down. So we have opportunities to harvest microbes that break down the materials. We can also take the enzymes out of those microbes and utilize them. We have insects that have eaten some of these plastic materials, developed gut microbiomes. So we have some sort of microbiome consortium type concepts. So there's different ways to handle the problem. On the build up, as long as we can get down to sort of a central, center of the wheel sort of molecule, we can take that a lot of different directions for use. So we can start to use cellular outcomes from microbes or even higher organisms like fungi or insects potentially, and make 3D printing material that Alessio can put into what he does. But lots of different approaches. I don't mean to dominate, but we can go into a lot more detail if you're interested.
So before I pass it on to Alessio, so do you use, you said that you go down to change their 8 to 14 carbons structure. You then feed these to the enzymes, so you don't use them directly to create food, right?
No, so there's a middleman in that, which is the microbes. And we have individual microbes. We can do synthetic biology to make them more efficient in their use. We could also use directed evolution. So basically growing them over and over on a new source so that they learn to utilize it more efficiently. But essentially what we're doing is, sort of tailoring a carbon source to a microbe or a microbial community. And then the utilization and harvesting of that carbon and the energy contained within those carbon bonds can be utilized for upcycling into other carbonic structures like other carbohydrates, fats, or protein structures if we have nitrogen available and things like that. So yeah, just using microbes to, ultimately produce what you need.
Thank you. Alessio, can you tell us a little more how your 3D printing works, and if you could actually print an apple?
Well, Nicola, not yet. No, I'm joking. So our 3D printers today work, of course, with our super polymers and composite materials, which of course comes from, oil. This is not a problem today, but it will become a problem tomorrow if we don't act today to let our technology being prepared to be sustainable, because of course 3D printing is more sustainable compared to mass production methods, because we don't need to produce millions of parts, and we don't need to store those parts for years in warehouses. So we use 3D printing uses just the resources it needs to create the parts. So this, first of all. And talking about metals, and especially CNC machine metal, of course, we don't need to create waste of materials, because we use just the material needed for the part. So 3D printing is more sustainable compared to mass production manufacturing methods like CNC machining, injection molding, and the other stuff. But the technology is becoming more and more adopted in the world. So it will arrive a moment where 3D printing will become part of the problem. If we don't create supply chain behind the recycling of the printed parts, and if we don't create today the right conditions for this technology to be adopted, to become a real sustainable manufacturing for the long term. So our goal today is to create a supply chain method and a business model which allows our customers in sending back the parts at the end of the life cycle and sending back all the scraps little scrap, but still scrap, like superstructures, raft, and all other things involved in the 3D printing process. Because it's not true that 3D printing is a zero waste process manufacturing. That's not true. Even 3D printing creates some waste. So we need to care about that. Okay, and our model behind the recycling allows our customer to make sure that all the scraps and all the 3D printed parts at the end of the life cycle will be recycled into new materials. We want to incentivize them to take care about this, offering the new material to them, the recycled material, the circular economy material, at a fraction of the cost of the initial one. Of course, we all know that polymers after recycling lose some properties. They lose some mechanical properties, but there are still an enormous amount of applications where thermal properties, chemical resistant properties are required, and you don't need that level of mechanical performance, even within the same customers. And the goal is to, democratize more and more the usage of high temperature and high performance technopolymers and incentivize the circular economy program we put in place. While we do this, we need to invest today to create the biopolymers and the biocomposite in 2, 3, 4 years from now. It's not easy. It's not easy, guys, because super polymers and composite materials like carbon fibers, PEEK materials, etc., are the result of years and decades of inventions around the world. So today we all need to be concentrated in developing the future generation of biopolymers and biocomposites. So polymers that comes from nature, because I firmly believe that nature has all the answers. We just need be capable to replicate what nature did in the last thousands of years in a laboratory and scale into industrial scale. This will require time and will require huge investment, but if we don't act today, we'll be still, victim of oil for the next 50 years. We cannot do that. We need to invest today.
Thank you. So one question that we got is, how quick are these processes? So Blake, how quickly can you break the plastic down and then feed it to the enzyme or whatever? And I'm a chemical engineer. When it comes to biology, I struggle. and then I have a question for both of you about how you could mix everything in a value chain where you go in maybe not for a war with just the fettuccine alfredo, and you start to break down all the plastic and you 3D print everything you need.
Yeah, so the kind of a big problem that we have in utilizing biology for most approaches ends up being the time that it takes, because biology, when compared to chemical approaches like pyrolysis, is going to be much slower. And then the other problem is always consistency and replication. Biotic organisms can be finicky, constrained by physics. So where you have temperature, issues, things like that, humidity, pH. So there are pieces of that we have to consider. But the speed, largely on the front end of the system, breaking down the plastic, we're using where we've used like the catalytic based approaches with a small amount of energy. We're able to almost instantly break down the materials. So in a matter of minutes. And then on the biological part of the process, it's much slower, but we're looking at approaches to potentially increase that time, either through genetic manipulation or the directed evolution approach. And so it's early stage research, so we have a ways to go. But what we're trying to do is sort of lower that bar of entry so that some of these other approaches can be de-risked a bit. On the back end, looking at the growth of the microbes, one touch point that we have in thinking about the microbial system that we use for making biological cement that ultimately leads to a cement alternative That usually grows on the order of 4 hours for large amounts of material. So we do have some ways that we can accelerate the production. And the goal in the program, and most most of the time in a DARPA program, when you put the broad agency announcement out, if people don't think you're a little crazy, then you're probably pitching at the wrong level of what you want to do. But we're really looking at having a continuous system that can, in the smaller footprint device, support 10 individuals over like 10 days. And so something that continually puts that in. Now, a lot of that's dependent on the amount of material that you have to put in on the front end. And the larger format, we're looking at something that could sustain a large group of people in the order of 100 for a 30-day period, continual production. So, you know, those are hard metrics to hit, honestly. And we're looking good. I think we'll get there, but you know, we gotta set the bar high so that we can really push the researchers to do something incredible.
Thank you. Alessio, how fast can you 3D print?
Well, I don't want to give numbers, because without the right context are not useful. But what I can say is that we can print in hours what today is produced after 3-4 weeks. Why this? Because today, you know, to produce a parts by CNC machining or by injection molding, you need to put in place the entire process. You need to create the molds. You need to do the first, the second, the third, the fourth interaction. And at the end of those interactions, probably you discover that you design not in the best way your part, and you need to start again. So we do today in hours what until yesterday has been done in weeks. But what we can do more, and what we do more every day, is to have hundreds of printers today in the world that can print simultaneously hundreds of parts. So in my opinion, 3D printing will never be fast as traditional manufacturing method, because, you know, the concept behind 3D printing was different from the beginning. So if we pursue the goal of realizing 3D printing technology capable to print or produce and they have the same productivity of an injection molding, that's not the right direction, in my opinion. 3D printing must ensure us the same level of performance, repeatability, and consistency of traditional manufacturing methods, which in my opinion, the business model needs to ensure us the scalability of the production. In our business model, we have hundreds of microfactories in the world that we can control, and we can ask with one click, 50 machines start to produce the same parts in different locations in the world. In my opinion, the business model is the real key to scale the productivity of the technology. The technology must be reliable, must be consistent, must create repeatable result and performing parts, while the business model should create the right scalability.
Thank you. Phoebe, you had some question from the audience.
Yes, so a question that we've received from the audience, we have a couple, so we'll just go through them. Firstly, could each of you say a few words about the cost of the processes that you're suggesting, 3D printing and resource? Thank you.
Alessio, you want to talk about the cost of 3D printing? Because my stuff's super early stage, so there is currently no cost other than the research funding that we're providing.
Yes, it's still expensive, in my opinion. And we really need to be careful about this. 3D printing is not cheaper, okay? Probably it's not more expensive than traditional manufacturing methods, if, of course, we compare apples with apples. So if we talk about the same numbers, the same parts numbers, it's not more expensive, but it's still expensive. The way to create a more affordable technology is to democratize more and more the technology, in my opinion, is the sustainability. So I firmly believe that sustainability is the key to democratize the technology, because in our business model, the more printed parts are printed by our 3D printers, by our customers, the more recycling we can do, and the more materials at cheaper price we can offer to our customers. This, in my opinion, is the key to democratize the technology, because oil-based polymers are expensive, because there are expensive process behind to create that. PEEK material is one of the most expensive polymers in the world, but it's one of the most performing polymers in the world. So we need to find a balance. We need to democratize the use of these super polymers while taking care about the recycling of those super polymers, and create a mechanism where we can offer these materials as a circular materials to the same customers and to other customers, to new customers, in order to democratize more and more the technology. And at the same time, we need to develop high performance biopolymers, which replicate the same mechanical performance, thermal and chemical performance, maybe one day, of these oil-based polymers. It's not easy. I mean, it's not easy, of course. But in my opinion, today we start to have the right tools, and there is a huge commitment today, even from customers, in adopting these super polymers. They are more open-minded today than ever before. So this is the perfect moment to invest in massive resources in this, because I firmly believe that biopolymers and biocomposites will be the future, will be way more cheaper than oil-based polymers.
Thank you. And Nicola, I don't want to put you on the spot, but could you also speak to maybe the relative costs of mechanical versus chemical recycling, to the best of your knowledge?
Well, in a way, it's an easy answer. The fact that it's not chemical is not being done today shows that it's definitely more expensive. But it also relates to the fact that if you compare virgin plastic to recycled plastic, sometimes the virgin plastic is still cheaper, especially when all prices are low. But I think, to the point that Blake and Alessio made, it's important to keep in mind that we do this cost analysis without considering a lot of the externalities that we don't factor into fossil fuel use. So it's like comparing apple with pears sometimes.
Yeah, and Phoebe, I was also going to mention, one of the questions that came up was about, breaking some of these molecules down. Currently, pyrolysis, breaks us down into the single carbon or ethanol space. And so what you end up with is a large energetic cost there. And if you sort of use the logic that we're approaching resource with, you have to develop those molecules back up 2 carbons at a time. And every time you reassemble, you utilize energy. So in the pyrolysis example, you're using a lot of energy, and then building something up is going to utilize more energy. And so our approach was really to break things down into, I guess what in the business world would be like the minimal viable product that we could get out of that breakdown process, and try to conserve as much energy as possible. And so, I think to Nicola's point, some of these alternative approaches, haven't scaled yet because we don't know, the sort of where the bounds are. And so with projects like Resource, we're looking into that and looking at the risks that come from it, and seeing where they go. So when I think about some of these technologies and how they're going to scale, DARPA, the agency that I work for, has always been very thoughtful about how do you produce something. That's one thing. How do we make the impossible possible? And then on the other side of it, at what point do you start, getting it into the market so that it can be useful? And one example would be, again, I probably come back to this all the time, but the concrete is a good example where traditional methods of concrete are known throughout the world. We've been doing it for a long time. I think the Romans made some pretty good concrete back a few generations ago, and it still stands. So it's a well-known, well-tried, very true process. So when you come in with something new, And in this case, like I said, we're on the right side of the carbon equation. People want to be on that, but they don't want to spend, 50 times, 100 times the cost to do something on a large project. So what we have to do is try to push towards scale, where the scale of our biological approaches or our alternative approaches, like Alessio was talking about, can actually meet the market demand while also being cost effective. And then I think if you're, within the same order of magnitude, then people would, want to use the more bio-friendly approach. But, for all of these types of things, we have to get there. We have to get it to scale. And that takes a lot of work and a lot of time. So whatever we can do to push that, will make the world a whole lot better place.
Alessio, we have a question for you. What is the optimal batch size for 3D printing per unit cost?
Well, very, very, very nice question. And the answer is, it depends. Because it can be 100, can be 1,000, can be 10,000. The real question is, when do you need these parts? You need more in the morning at 8 a.m. or you need on monthly basis? Because the real thing is how many parts I need in this specific moment. Because you can have the need to have probably 10,000 parts per year, but you don't need 10,000 parts Monday morning at 8 a.m. You need 1,000 parts per month. So the real question is, how can I produce these parts in a smarter way? How can I produce my parts on monthly basis instead of producing all these parts in just one shot and with traditional manufacturing methods and wait 1 year to use my parts? Because so this is the real question. The timing is the most important thing, because if you need parts and you need these parts split in a year, the most sensitive thing could be probably produce this part, even if the number seems to be high, produce this part with 3D printing, so you can produce just in time on monthly basis, avoiding warehousing costs, production costs, setup costs, and all the things involved.
Blake, have you tried the food coming out of the resource process?
Good question. So technically, on a presentation to the public, no, because it hasn't been through FDA approval. So no, but so just to show you some of the materials. So this is plastic. On the front end, not much really there, but what we do is we break that material down into those smaller carbons. Doesn't like to focus, which that's sort of a slurry of DCAs that are the middle part of that process. And then what we ultimately do is grow that into what looks like, a granola bar that is made of cellular material. So but this is just one approach. We also have been able to take the material at the cellular material at the end, and we can actually separate out parts of that. So we can pull oils out specifically. So we've been looking at lubrication needs, machines, things like that, as one of our endpoints. And we even have some pretty cool ways that we can get the microbes to excrete that fatty acid material, and we can collect that. And if we use molecular biology, we can tailor that to specific chain lengths in fatty acids, so you get different capabilities there. So we haven't used any of it in practice officially, and it smells good, I can tell you that.
That's a good way to answer it. It smells good.
Yeah. I mean, it's really, if you think about yogurt, production, that's made by a microbe. That's sort of the end product that we can hope for. Or I don't know how old everybody there is, but it's also how beer's made. So we might be able to make some additional products out of the system.
Okay, I think we could go on for hours, but the time we're out of time. So Blake, Alessio, thank you so very much for your time and all your insights. Thank you. Phoebe, thank you for your help, and thank you to everyone for taking part in this. Bye.
Thank you so much for inviting us. Thank you.
Have a good day.
Thank you.